The last speaker, again a grandson, is Dr. Advait Chhatre, who did his PhD with the son, Professor Anurag Mehra of IIT Bombay. Nilesh, after doing his BTech, did his masters at ICT, then worked with MaxPro United Phosphorus, Enginero, Pidilite from about 2005 to 2009, but didn't really like it. So he took admission for PhD in IIT Bombay and completed his PhD work in the period of 2009 to 2016. I was fortunate enough to examine his thesis, so I know a bit about his work, and you can see how a complex process of crystallization and the population balance can be exploited for the industrial design of crystallizers. Dr. Advait Chhatre.
Thank you, Professor Pandit and Professor Joshi and Professor Anurag Mehra for giving me this opportunity. So I'm moving ahead with the topic, the mysteries of anisotropy in nanomaterials. So anisotropic nanomaterials are very interesting because they have large surface areas and they have a number of kink sites which makes them useful for catalytic applications, as well as the same reason of having the large kink sites creates an unique optical responses which are nowadays more useful in the medical imaging. So there are a few strategies that are used for obtaining the anisotropic structures. For example, having a templated growth, or using templates for the growth, self-assembly, and milling down the macrostructure to the nanostructure. Now, this is the schematic I am providing. This is a generalized mechanism in which where the anisotropic structure is formed. So this consists of attaining supersaturation, nucleation, then particle growth. Now particle stabilization is an important step because at this length scales the particles have very large surface energy and they need stabilization for preventing spontaneous aggregation, as well as there is a morphology selection. So in this talk I will be talking about more about how to model a morphology selection, and I will take two case studies. One is the directional growth controlled by a surfactant, and then self-assembled kind of growth. So in the gold nanoparticles, this is a protocol that is quite famous. It's called the Murphy's protocol, wherein the nanorods are made in 3 steps. In the step number 1, precursor and surfactant is mixed to create a growth solution. In the step number 2, the seeds are formed by using a very strong reducing agent, and in step number 3, the small amount of seeds are added to the growth solution to get the gold nanorods. So the colors of these boxes are approximately representing the colors of the solution that we are getting. So there have been a few hypotheses about how these particles grow. So first of which was typically a cylindrical particle is there, and there are 2 differential growth rates to create the particle. But thing is that this particular hypothesis is not giving us any morphology selection, and it is observed that a mixed population is always found in the system. Now based on that and a few other experiments where the crystallography of the nanorods and the surfactant structure on the particles was found, mechanism was formulated by Murphy's group. So what happens is a spherical particle will develop the facets and undergo some develop a structure that is intermediate. So it is a structure which can grow into anisotropic form, and afterwards that the horizontal surfaces, that are the surfaces marked by 100 planes, will get capped by the surfactant to arrest the lateral growth, and eventually the growth of the system will produce the nanorods. So a very critical step in this is the shape selection. Shape selection happens with the formation of a decahedral structure like this. So this decahedral structure is a very unique structure. It is formed by all the faces are formed by the 111 facet. Now that is a energetically most stable facet in a crystal. However, there has been one contradiction with the experimental data, that all the particles are not forming the rods. So like for example, if this particle has to form the rod, all spectrum of the diameter should get, but there is a very narrow diameter spectrum that we are getting. And to address that, there is, if we look into the details of it, and if we join the tetrahedron, theoretically tetrahedron cannot fill the space, and there is a gap of 7.4 degrees that is remaining. Now this gap, for filling up this gap, the particles or the atoms at this edge need to undergo this training, and that adds to the energy of this structure, and the benefit of lowering the energy that we have gained by having the low energy facet is now lost, and because of which it creates a situation like this. So the particles will start growing, and in a particular because of these two counteracting energies, the structure will be stable in some intermediate form, and these particles will start growing within the nucleation window, what I will say, under which the particles are stable. Only in that part this particle can transform into the nanorod nuclei, which can then further go to the nanorod. If the particles keep this window, then they will not form the nanorods, and they will keep growing as spheres. So based on this, I formulated an initial mechanism where I could get a sphere to cylinder to rod, and writing down all the diffusion and reaction equations, which I am not showing here. So, and I think it is not visible, but I will just mark it. So what I got is the experiment versus simulation. So this, the red line. Now the actual experimental curve is like this, but the simulation line is going like this. So it was not matching. So something I missed here was I approximated this structure as a cylindrical structure. So then I added that detail. So I approximated that structure, the decahedral structure, as a biconical structure, and then I get a very nice fit with the experimental data. And in this graph I am showing the effect of seed size. Again, the red line is for this particular system, and the black line is for this system. This dotted system is the data of a third party, that was published by somebody else in the literature. So going ahead, now none of the models have that were developed until now had the ability to predict the yield of nanorods. So in this model, our scheme, the nanoparticles, spherical nanoparticles growing, and some of them forming nanorods within a particular area, is making us ability to predict the yield. The key parameter is the time of residence of a particle within this window, and the time which takes for the entire population to get converted into nanorods. So that ratio actually defines how the yield of the system will evolve, and that is, you can see that it is a very highly correlated structure. So moving ahead to the next part, the self-assembly part. There is a system that was developed by one of my friend Vinod Gupta in our group, and the step had three simple steps: preparation of worm-like micelles, and introduction of spherical particles or preparation of spherical particles in situ, and allowing this mixture under aging for understirring for about 24 hours, and then he got well-formed nanorods. Now the surfactant, whenever surfactant micelles is added with sodium salicylate salt, this salt occupies the interstitial space and reduces the head-to-head repulsion, and that helps the length of micelle to grow. And because of which this particular micelles show the viscoelastic nature, and they form they are just like resembling the polymeric systems, and they undergo this slithering motions. Now to model that, several set of experiments were carried out, first of all we did without WLM, without having worm-like micelles, without having shears. In this case we found worm-like micelles and shear both have the necessity for formation of the nanorods. Then spherical particles to nanorods. Always there were spherical particles were observed in the form before getting the nanorods. So based on this, we formulated a mechanism. So in this system of worm-like micelles is sitting there, and the particles are adsorbed on the worm-like micelles. Now these micelles, when subjected to the shear, they undergo the reptation and the slithering motion, and while doing so, the particles that are absorbed on the micellar surface, they come together, and when they come together within the radius of their interaction radius, they now start hopping from one micelle to the other, from a lower mass to a higher mass. So that was the assumption we made, and then we tried to see whether we can get a particle estimate from this, particle simulation on that. So I am just actually very fast forwarding this. Why should a particle should adsorb on a worm-like micelle? So worm-like micelle will actually make a cage like this, and this is about 4 diameters long, and this dimension we get from the rheological measurements. Now this, if we see, there are two types of diffusion coefficient. One is the intra-cage diffusion and one is the inter-cage diffusion. Now intra-cage diffusion and inter-cage diffusion, if I calculate the time scales, there are order of magnitude differences over here. This is of the power of -6, -2, and so on. So because of which the the worm-like micelles actually arrest the spontaneous aggregation of the particles and keep them adsorbed on this, adsorbed. So now next comes is to how to do a model on that. So the model is not possible on a very traditional way, but a lattice model is possible. So we created a lattice model in which we are representing the WLM by a flexible polymer, and the particles are represented by a small dot here. Now if we see, there are two length scales happening here. The length scale for the micelles is this Kuhn length of a micelle. So whenever a micelle will move, it will hop this much distance from the lattice. However, whenever a particle will move, or a R cut for the particle to particle interaction will be 2 lattice positions. So because of which this simulation gets into a multi-scale lattice simulation, and eventually we could get to predict the simulation results. We could capture the effect of precursor concentration. We could actually capture the effect of shear. Now the shear was compared with the experiments by equating the Peclet numbers in the experiments and simulations. Then this was a theoretical study, because variation of Kuhn length was actually difficult in doing experiments. So what we found that the Kuhn length has a very strong effect on the dimension of the particle that we are getting. Now why? Because whenever we are increasing Kuhn length, the pervaded volume of the polymer is increasing, and as the pervaded volume is increasing, the frequency of interaction between the particles adsorbed in the micelles is also increasing, and that is why the particle-particle interactions are increasing, and because of which our particle dimensions are also increasing. So in the summarizing this, what I say is a mystery element in the shape selection is, in case of the gold nanorods, it was the crystal twinning, the tiny 7.4 degrees gap in the twinned crystal, and the competition between the growth and the twinning. That is found to be the key element towards morphology selection. Whereas in case of WLM, there was a particle to WLM interaction, particle to particle interaction, and the shearing, slithering of the WLMs that was found together. So I say thank you for giving me this opportunity.
Thank you, Advait. Can I request Professor Sharma to hand over a small memento to Advait? As you can see, the basics are still strong, and the kind of culture which was developed starting with the science and then ultimately extending it to application continues.